Good morning, everybody, and thank you for inviting me to this very interesting conference. It's quite a multidisciplinary conference, obviously with a major focus on high-performance computing. And what I'm going to talk about is the work we've been doing for, 15, maybe 20 years now to really push the frontiers of using high-performance computing to tackle really complicated biomolecular systems. And by that, I mean systems that have, lots of proteins. They're doing things. Viruses are one of the main topics of interest to us. I think many of you may be aware that computer simulation has been very important in protein science and bioscience. And the 2013 Nobel Prize was largely given for doing molecular dynamics simulations of proteins, solving Newton's equations on a computer. And that was tied very much to, crystallography, to nuclear magnetic resonance, different experimental techniques. My goal, and of course I'm not alone in this, is to really push these sort of physics-based ideas to higher scales so that we can begin to address problems of significance in cellular biology. So things that involve hundreds or thousands of proteins, membranes, things important like relevance to cancer or to viral infection, and I'll show you a number of examples with the viral infection. Coarse graining is the topic. Let me just quickly back up here. If you look at this hierarchy, these are actin filaments. So these are core structures in your cells, and they're made up of this protein actin, which forms filaments. You can see those filaments over on the left. And if you try to do all atom studies, highly resolved atomic studies, just going to a small segment of a filament, which is there's 13 proteins here, that there would be solvent, you hit 1 million atoms immediately. So to go up to these higher scales, it's going to require something conceptual. And that is what we call coarse graining. You can see here in panel C, a simplified model. And it's a model where we represent whole parts of the protein by simpler objects. And the key is, how do you do that without throwing out the critical information? So this has huge implications for physics, for machine learning, for high performance computing, for lots of things. Okay, so what we really sort of pushed 15 years ago was the idea of what we call bottom-up coarse graining, that we wanted to stay true to a molecular description. And in my line of work at statistical mechanics, we want to understand things about the Boltzmann distribution, about how things at a constant temperature function and move, and their connections to thermodynamics and to structural data that you might measure experimentally. So coarse graining, the idea of bottom-up coarse graining, we want to maintain this statistical mechanical connection, right? And in principle, that means sampling over many degrees of freedom. This boldface R is a vector of all the particle coordinates in the system. This is the potential energy function that ultimately comes from quantum mechanics, how they interact with each other. And what we're trying to do here is to map, this is a little hairpin peptide, into a simpler structure where we map whole pieces of it into things we often loosely call beads or quasi-particles. They represent whole parts of the protein. And the big question is, how best to do these mappings? This is increasingly a very important question for machine learning. How do we understand the information we have and that we're losing, right, to find these best maps? And then an even harder problem, once you've done that, is what now is the effective interaction of these new sort of quasi-particles? I'll call them beads, these coarse grain beads. It looks a little bit like a necklace. So we did work on this some years ago, and we're able to largely, at least formally, solve this problem and practically solve this problem. However, in going to this higher scale, it's not good enough. The coarse grain model that I just showed you is still too highly resolved. It's got too many of these coarse grain objects in it. So we need to get very aggressive in how we represent our coarse grain systems. And for example, you see this actin protein. This is what we call an ultra coarse grain model. It's very highly coarse grained, but it's more elaborate than that, okay? So what we have done here is we've represented a whole protein by 13 of these quasi-particles. And the question is, what is this object? Is it, do you treat it still like a Newtonian object? And the answer to that is really no, you can't do that. It's too highly coarse grained, and you're trying to describe too much physical behavior by a very simplified model. So to make a long story short, in my early days in science, as I started, as a faculty member, and also even before that, I was a quantum mechanic. So I studied a lot about quantum mechanics, doing quantum dynamics. And of course, in quantum mechanics, you have these quantized states. Everybody's interested in quantum information these days. You have these quantized states. So it occurred to me that there's an isomorphism here with what we needed physically for these models. And that is, the idea is, don't treat them like Newtonian objects, just like these particles have F equals ma, you integrate their motion, maybe you put some friction in there. Treat them like quantum mechanical objects so that each one of these particles also can have internal states, embedded states that describe realities that are going on. So an example here is this gold ball is the nucleotide can be in three possible chemical configurations: ATP, or you have a hydrolysis reaction, so you've broken a bond, you have a phosphate still bound, or the phosphate has dissociated and you have ADP. And so this gold ball really needs to have three states embedded in it, and those three states, their kinetics and what they're doing depends on the conformations of these other ones, and they in turn depend on what state you're in. So it's a highly coupled, non-trivial problem. But the beauty of it is you can really coarse grain the system while retaining a lot of information. So this was a breakthrough we did now, 8 years ago. And the idea is we can describe lots of things that go in biology with these very coarse grained models. And this has had a huge payoff for us. So I'm going to spend most of the rest of my talk talking about some applications of this and also some high performance computing implications of it. Let me first talk about HIV. So HIV, before the coronavirus came along, was a thing that really people focused on probably the most, and I hope they will again too. HIV involves a relatively simple cycle. Viruses are parasites, right? They use your cells to replicate themselves. So HIV kicks out these what are called gag proteins. HIV has an RNA that encodes the virus, and what happens is these proteins assemble in the infected cell. They bend the cell membrane and create a thing called a bud. So they give birth to a new virus particle, and all viruses do this in one way or the other. And then this virus particle goes free, and a very fascinating chemical process goes on in here. An enzyme called HIV protease starts chopping up the gag, and then a piece of the gag self-assembles around the RNA. This is called the virus capsid. So we felt with all of these fancy techniques we have, we should be able to study this very complex self-assembly process, in part also because you can do it in vitro, in the laboratory. You don't have to do it just in biology. You can take these proteins and some salt. You don't even need the RNA. You can put them in a test tube and you can form these capsids. So we figured, this is controlled enough that we can do this. So this paper was published, I guess now 5 years ago in Nature Communications. And this is a picture of what the HIV capsid looks like. This is before this cleavage, this is after up here. It forms this interesting cone-like shape of these hexagonal lattices. And what happens when the HIV protease cuts up this protein, you get these segments here, which are called the capsid monomers. They dimerize into a dimer. This C-terminal domain has a very strong binding, and then they assemble into this lattice. And it's a really complicated lattice because one half of one of these proteins is in one hexamer, the other half is in an adjacent hexamer, and then this C-terminal domain, this gray domain, is kind of a shell down. And if that's not complicated enough, you also need some pentameric defects. These red spots here are not different proteins, they're just assembled in a pentamer. This is called Euler's theorem. In order to close this surface, you need these pentamers, and in fact, I believe it's 12 of them you need, okay? So we were brave, and I should say my postdocs were brave to try to do this. And there was a problem we had to solve, and I'll have to go through this really quickly. In these simulations that we do, the solvent is no longer there explicitly, it's implicit in the interactions. In principle, there's a lot of space that's empty. In many simulations that are at these very coarse-grained levels that are can be so impactful, we have a lot of empty space. So traditional load balancing methods really were not well suited for this. These methods that are used, for example, in molecular dynamics simulations, where we have a pretty densely filled space. So what this postdoc at the time, John Grime, was really a brilliant postdoc. he learned about using methods that, for example, had been developed in astrophysics, where you have a lot of empty space, obviously, you have galaxies interacting with each other. And these are Hilbert space-filling curves. So John, back at the time, actually adopted this, wrote from scratch his own code so that you could load balance and scale over thousands of cores in doing this, these Hilbert space-filling curves. Here's an example here where you have large parts of space are empty or mostly empty. Here they're clustered as if they're assembling. And how do you load balance in that? And John was able to adopt these methods. And in fact, I should mention that this has been largely implemented into the LAMP's molecular dynamics code, these approaches. So it's really been a big payoff for us. So let me show you where the ultra coarse graining came in, and the first outcomes of these simulations. These were, no one had ever approached this kind of thing. You're effectively simulating billions of atoms with these models. What we found was something incredibly important and also something very heartbreaking at the same time. This diagram here shows you what you might call a phase diagram. This is the concentration of this assembling protein here. And this is a crowding agent. In experiments, you need to add an additional crowding agents, which are basically little polymer balls to help facilitate this assembly. And the important thing John found was that a key nucleator of this lattice growing were these trimers of dimers here. So what you see is 3 of those dimerized proteins in a little triangle. So there's 1, there's 2, there's 3 color-coded. And they come and go all the time. They're the nucleators. Any growth of a lattice process, like the freezing of ice, needs a nucleator, something nucleated. And down in this quadrant here, that's all that happens. Nothing happens. But when you push across this boundary here into either higher concentration or more crowding, something starts happening, all these pictures, but something happens out of control. It's completely too much. You start growing these lattices. You can see the hexamers here. The blue guys are these trimers that are templating, growing the lattice. But it was out of control. It just wasn't right. We had something wrong. So, we had discovered something really important about this assembly problem, but we were not getting the right answer. Never. Okay, you could run hundreds of these simulations. So what we realized is, surprisingly in hindsight, we had missed something that was really a little bit dumb. If you look at this protein dimer, this thing that's assembling into this particle, this is just one possible conformation. This is very loose linker here, right? So these whole helical bundles can flip around on each other in solution. They can be in many different conformational states. And in fact, only this state is the one you need to be in to assemble, but the others are possible when this thing is floating around in solution, hundreds or thousands of them. Incidentally, there's about 600 of these protein dimers in that assembled capsid. So fortunately for us, there was already NMR experiments, nuclear magnetic resonance, that had sampled these distributions in solution. And it turns out that only about 5%, maybe 10% of the time, is this protein in the right conformation to be adding to this protein lattice. Okay, the rest of the time it's in the wrong conformation. So if it interacts with this growing shell, it's not going to stick. Okay, it needs to find the right conformation. The problem is you cannot possibly explicitly sample these conformations in this coarse-grained model. You would burn up tons of computer time just doing it for a single protein, let alone 1,200 of them, 600 dimers. So what did we do? Well, this is where the idea of the ultra coarse graining comes in. You can define a variable that, in this case, you can get directly from NMR experiments. You don't necessarily have to calculate it, but it just tells us that we're in the right conformation or we're in all these other conformations that's not right. So this variable comes along for the ride and switches on and off with the right statistics, the right time scale, this conformational equilibrium. So it's a kind of in an engineer's language, kind of a subgrid variable that comes along with this coarse grain model. And when we do that, lo and behold, you still find regions where you don't get good solutions. This is a slightly different graph table here. This is time scale of the switching, and this is the percent of active. Remember, I told you about 5%. But if you tune things just right, you get the proper assembly. And this movie. So this movie shows the assembling proteins, and I'm only showing the proteins that are going into this assembling capsid. It's a very dense structure. There's lots of crowding agents. There's lots of free proteins. I'm just showing you the growing capsid. And what you see here is these trimers up here in the upper left are templating the growth as they're supposed to, right? As these proteins pack into this lattice, there's curvature. So this fortunately plays again. There's curvature that they naturally, the way they pack into these green hexamers, curves that lattice. And a third kinetic process is the trapping of these pentamers that is required to finally close this structure. So what you see here is a what we call a kinetic funnel. Okay, this funnel is basically you need these three things clocked properly to assemble. You need the right assembly rate of the lattice, the right curvature rate of the lattice, and the right trapping rate of the pentamers to grow these things. Okay, and so that was a really a major discovery. Now, why this is important beyond clear scientific interest is what's it all about? So one way of understanding that process, this is oversimplified badly, but if we imagine some sort of a parameter that tells us about the lattice growth, okay, it tells us how many lattice contacts we're growing. So we go this way. If you look at the free energy of the system, many of you may have taken, general chemistry or courses beyond. The free energy is minus T, the delta S is the entropic part. So when I take these proteins out of solution where they have tons of freedom, entropy, and put them into the lattice, delta S has got the wrong sign. It's losing entropy. And the second law of thermodynamics tells you that shouldn't happen. So minus T delta S makes this go up. If it were entropically defined only, it would never happen. But when they go into that lattice, they form contacts, right? The proteins interact with each other. That's just pure energy. That's the enthalpy is negative. So that's that slope. So what happens is you get a turnover. And the rate of that growth is a so-called Arrhenius law. It's an exponential law with this free energy barrier divided by constant times the temperature. And it's incredibly sensitive. So we were not getting this right in terms of this growth because there's alternative pathways also that need to happen. I told you about these kinetic funnel, and if they're out of sync, it screws up everything. So why does that matter, and why do these simulations matter? It turns out that the good scientists, both at Pfizer and at Gilead has had more success with this, also understood that maybe a way to interfere with HIV is not to try to stop every binding event. Traditional drug design is to inhibit something, send in a small molecule that binds in an enzyme and stops it. What they realized is that's going to be really hard to do with 1,200 proteins here, but what they might be able to do is glue together some of these proteins in these critical structures and over-accelerate the assembly process. And I visited Gilead shortly after we published this paper, and I met with the whole HIV team, and they said, you've explained to us how our drug is working. This is fantastic. And what's basically happening is that their drug, which binds up some of these dimers into a more stable thing, throws off this kinetic funnel. And in fact, we see that. We published this paper a few years later. This is a somewhat jumpy movie. This is what I showed you before of a forming of a normal capsid with no drug loading. You can see the shell, the closure. Okay. This now is just a few percent, and it starts throwing off the kinetic funnel. And you start seeing, first of all, it's not really a cone. It's it's got some holes in it. The pentamers are all in kind of the wrong place. And this one is even more drug loading, something like 5%. And you can see this capsid now it's got major problems. It's got holes in the lattice. It's not going to incorporate the RNA properly. And so what computer simulation did here basically, which I think is really valuable, we were really excited, is explain a whole new concept in pharma, basically, of not trying to stop some process, but hit the accelerator, make it go too fast, and crash and burn, basically. And this, they're already looking at this for hepatitis. I don't know about coronavirus yet. I think coronavirus right now is so new that we're not sure. I'll come back to that. So, well, actually, I won't. Here it is. So in the last sort of 5 minutes, let me tell you about our efforts on the coronavirus. like so many people, wanted to see if we could contribute something to the coronavirus. In part, just because it's an international tragedy, we thought maybe there's something we could do. But scientifically also, there's such a huge push that there's new structures being resolved almost every week. You'll see this, and new simulations of individual proteins. So we thought, well, can we do what we do best? Take all of the data that we can get, and it's going to be time dependent. There's going to be more and more of it, and do these coarse grain models of this virus particle, right? The so-called virion, the thing you've seen ad nauseum and on the news over and over again, right? With these spike proteins. And so what we did is we took in the so-called viral envelope, right? There's 4 key proteins. There's the S protein, which is the target of the antibodies and of the vaccines. There's an E protein, which is thought to be an ion channel. There's an M protein, which is important for assembly, and the N protein, which helps bind with the viral RNA. So these are key structures that we could put together. And we were able, this paper just came out in Biophysical Journal earlier this year. We were able to put together the first sort of complete, what I'll call multi-scale, because we did take a lot of all atom data in building this coarse grain model, not just an ad hoc thing. These graphs here show about structural correlations in these spike proteins compared to doing atomistic calculations, and it's remarkably good. And the reason we do this is that it's not just to develop a nice movie, but it's to actually understand the cooperative behavior of this. So the thinking is that you need multiple of these spike proteins binding with these ACE2 receptors, right, in your healthy cells in your airway to do this process. And this paper now is under preparation. We've developed a coarse grain model for the ACE2 for the spike protein. All of this is bottom up from molecular dynamics data. This is not yet in a full virion model. It's kind of a patch where we have a membrane, we have the ACE2, we have the spike protein. But look at what we see here. What you'll see in the movie I'm about to show you is the first ACE2 will bind to one of the spike proteins, and it will kind of weaken it because it will sort of stick to it. But then a second ACE2 will bind in a particular direction and open it up. And then the second ACE2 will drag away one of the pieces of the spike protein, and the rest dissociate. And the reason that all of this is important is, I'm just about done, is in the fusion process. So this is a schematic. This is just a guess of what was happening. I'll show you what goes on. Is there's multiple interactions, and ultimately it exposes the spike protein to do fusion with your target, your ACE2. Okay, so what happens? Here's the movie. I have membrane up here. I'm not showing membrane down here. I'm not showing there's spike and there's ACE2. You see 2 of them. They're unraveling this thing in counterclockwise. Okay, and we have a dissociation event. It's scrolling through again and doing the same thing. And again, these are calculations that presently would just be impossible to do with an all atom description, and we can actually see this cooperative behavior. And of course, what's important is to statistically do many of these simulations. This is basically what you see happening here is there's an ACE2 interaction that helps in a particular directionality open up these things, and then ultimately there's a dissociation event. And if we plot the concentration of ACE2 over the concentration of spike, you can imagine different ratios. You see different behaviors, but this is an interesting one. This is a binding event, which is kind of sigmoidal. So you see that that as ACE2 ratio increases, we have a strong sort of uptick here in the binding. And this is important for a couple of reasons. One is everyone is scared to death of these variants. So we believe that we can translate the molecular information on, for example, the B117 variant into these models and understand, does that increase cooperativity? Is it simply a local event? What is the core Achilles heel of these variants that we might imagine, either new vaccines or new antivirals will need to target? Another thing which is a bit sad, I think you probably heard in the news that these poor minks, both in Denmark and in the United States, that they had to be killed in huge numbers because they were terribly infected by coronavirus. They have a very high expression of ACE2 in their airways. So you can see that the ratio of, if you have a lot more ACE2 here, that you actually get a very strong interaction. So This model is sort of one of the kind. I'm very excited that many years of effort in terms of this coarse grain modeling has finally got us to this point of doing something of this significance, and also with HIV. So let me just finish by saying these are the two wonderful postdocs that did the work. Alvin, you did the coronavirus work. Alex did the HIV work. The funding came from the National Science Foundation through a RAPID grant, which was absolutely indispensable, and secondary, some of the membrane problems of the NIH. And with that, I thank you for your time, and I hope you found this interesting.